Namaste. This is Natarajapillai again. So far we had a discussion on hypersonic flow, and now we have moved from saying the hypersonic flow by rule of thumb that the Mach number is more than 5 or 6, something like that, to the point where we can say if the phenomenon such as thin shock layer, entropy layer, viscous interaction, high temperature flows, the temperature is high enough to dissociate the air into ions, then we can call that particular flow as hypersonic flow. So here now, in that particular phenomenon, one more phenomenon we will consider is low density flow, right? So I acknowledge John D. Anderson's hypersonic and high temperature gas dynamics, right? This is a text which we use for this particular course. So now I will discuss about the low density flows. Okay. We had a discussion already on thin shock layer, entropy layer, viscous interaction, high temperature flows, and now it is low density flows. Okay, so basically we know that the hypersonic flight is usually happens at a high altitude, even at low altitude for missiles and all it happens, but in general increase in altitude, we know that the density will be keep on decreasing, right? So we have studied in the international standard atmosphere sometimes back in the introduction to aerospace engineering. So the basic point we need to consider is increase in altitude. At higher altitudes, the hypersonic flights experiences the low density flows, right? So here, the governing non-dimensional parameter in this particular regime is called the Knudsen number. Okay, so Knudsen number is basically defined as the ratio of mean free path to the characteristic length of the object, right? We know Reynolds number, Mach number, right? We have studied all these numbers, Prandtl number, and so on. In this case, for hypersonic flight, our point is Knudsen number. Okay, so Knudsen number is defined as the ratio between the mean free path and the characteristic length. Here, mean free path is termed as the mean distance traveled by the fluid molecule between two successive collisions with the other molecule. Right? So, one molecule with another molecule, that is what we mean, right? The mean distance traveled by the fluid molecule between two successive collisions with other molecule. Right? Now, characteristic length. What is characteristic length? Say characteristic length is, in the case of circular cylinder, we consider the characteristic length as the diameter of the circular cylinder. Airfoil, we consider the characteristic length as the chord length. Here, the characteristic length we consider as the length of the hypersonic vehicle, right? So we can consider the length of the hypersonic vehicle as a characteristic length in this case for calculating the Knudsen number. Right? So Knudsen number becomes an important parameter in this flow regime, where it is defined as mean free path to the characteristic length. Since the density of air is very high on the Earth's atmosphere, right? Earth's atmosphere or Earth's surface, the density of air is really very high. So if you consider the density of air is very high, then the mean free path becomes quite low, and then the Knudsen number becomes almost zero, right? So in ground, in Earth's surface, if you measure, the Knudsen number becomes almost zero. But if we consider any standard hypersonic flight, say taking off from the Earth's surface, right? we know that it encounter the change in density with increase in altitude. Of course, when the vehicle moves from the Earth's surface to the orbit or to the higher altitudes, the density changes, right? So, at the standard sea level condition, we can consider the lambda, that is mean free path, it is 2.176 into 10 power minus 7 feet. It's quite small, right? 2.176 into 10 power minus 7 feet. Hence, I consider on the Earth's surface, the Knudsen number is 0, right? So, at sea level, if you consider the flow is continuous or the concept of continuum is valid. So it is like we can say Anderson's way of saying is like when you wave your hand, correct? When you wave your hand through the air, you can feel, right? The gas you can feel, something like water, right? Water is high density with 1,000 kilogram per meter cube. When you just make your hand in the water, you can feel the flow or feel the continuity of the water. Similarly, air also we can feel at times, right? But in all our cases, right? Say in most of the aerodynamic problem, we consider a continuum concept, right? So that is what we say. More than 99.9% of all applications, right? We assume the continuous medium. Starting from our incompressible flow discussion and starting from all our aerodynamic calculation, compressible flow, wherever we studied aerodynamics, we consider the continuum. The flow is continuous. That is what our point, right? Now, imagine we are at an altitude of 342,000 feet. So here the air density is very much lower, right? So the mean free path is really much larger than the sea level. So there is a discussion that at 342,000 feet altitude, the mean free path lambda is 1 feet, right? But you remember when we calculate the mean free path at the sea level, it is 2.176 into 10 power minus 7 feet, but now it is 1 feet at 342,000 feet. So now when you wave your hand through the air, you will be like feeling like individual molecules impact on your hand, right? You cannot feel this as a air, or you cannot feel this as a continuous substance, but you may feel like something is hitting, correct? Some particular molecule is hitting your hand, and every time it hits, it has some interval, right? So under this particular situation of the lambda is equal to 1 mean free path, the aerodynamic concepts equations results based on the basic assumption of continuum will not work, right? In fact, that fails, right? Because the flow is continuous in our basic discussion in the previous calculation. Now the molecules are hitting. So at this stage, we need to approach it in a different point of view using the concept of kinetic field, right? So this particular regime of aerodynamics is called low density flow, right? We had a discussion on thin shock layer, entropy layer, viscous interaction, high temperature flows, and now low density flows. And the density is quite different, right? At the sea level, we found that the density is very high and the mean free path is in the order of 10 power minus 7. But at the altitude of 342,000 feet, we have a mean free path of lambda is equal to 1 feet. So one molecules hit at your hand, and the second molecules, the distance between the molecule probably 1 feet. So this particular case, the basic aerodynamic concepts and assumptions fails, and hence we go for a different point of view, and we use the concept of kinetic theory. This particular regime of aerodynamics is called low density flow, right? Now, so the validation of continuum assumption and the usage of the basic governing equations remain intact till the altitude of 90 kilometer only, right, from the Earth's surface. So from the 90 kilometers from the Earth's surface, we can calculate and say that the Knudsen number is below 0.3, right? The Knudsen number is below 0.3, and above, say, at the altitude of 150 kilometers from the Earth's surface, the density becomes lower, as the effect of fluid velocity and temperature at the surface do not remain in equilibrium with the surface. This happens at 150 kilometers, right? Now, there is a point, right? Say the flow of Knudsen number between the range 0.3 to 1 is treated as a transitional regime, right? Say we found that after 90 kilometer altitude, up to 90 kilometer altitude, we can say that the Knudsen number is 0.3, and till 150 kilometer altitude, we say that the velocity and temperature of the surface do not remain in equilibrium with the surface, and we say that the Knudsen number in the range between 0.3 and 1 should be treated as a transitional regime, where the slip wall boundary condition should be used along with the usual governing equation based on the continuum. So here, above 150 kilometers from the Earth's surface, the density become very low, and I told that there is a molecule hitting, right? You experience that the molecule hitting your hand, hence we should consider this as a free molecular flow, right? So here free molecular flow definition is where the Knudsen number becomes more than or equal to 1, right? If the Knudsen number becomes more than or equal to unity, we can call that as free molecular flow. Of course, we know that we have considered a low density flow, right? And then when the molecular become free, and when the when the Knudsen number become unity or more than unity, we consider this as free molecular flow. So at this particular flow, we have a lot of other issues, right? Say for any given flight vehicle, as the altitude progressively increases, right? So here the density decreases and the lambda increases, right? What is lambda? Mean free path, right? So the assumption of the continuum flow becomes channel, right? So it is necessary to consider in a different way. So an altitude that can be reached when the conventional viscous flow no slip conditions begin to fail. So specifically at low densities, the flow velocity at the surface, which is normally assumed to be zero because of friction, right? So it takes a finite value, correct? So this particular condition can be called as velocity slip condition, right? So we note that velocity slip, and we will discuss about the temperature slip and all. So note that this is a velocity slip condition need to be considered, right? When we fly at a very high altitude where the density is so small and the lambda starts increasing, right? So here an altitude can be reached where the conventional viscous flow no slip condition begins to fail, right? So this case we consider as a velocity slip with a finite value of error. Okay, now in the similar fashion, we can say that the gas temperature at the surface, which is normally taken as equal to the surface temperature of the material, now it becomes something different, right? So because you have a finite velocity on that particular point. So this is called temperature slip condition. Okay. So we remember we have discussed about the low density flow, free molecular flow, low density flow based on the decrease in density, free molecular flow basically considered because of the Knudsen number ranging from one or more than one, and velocity slip, and now temperature slip. So at the onset of these slip effects, the governing equation of the flow are still assumed to be familiar continuum flow equation, except with the proper velocity and temperature slip conditions to be utilized as the boundary condition, right? However, as the altitude continues to increase, there comes a point where the continuum flow equation themselves no longer valid, and the methods from kinetic theory must be used to predict the aerodynamic behavior. Right? So, increase in altitude, decrease in density, increase in the mean free path, and all those things we need to consider the kinetic theory instead of the continuum process simply. So finally, the air density becomes low enough that only few molecules impact the surface per unit time, right? And after these molecules reflect from the surface, they do not interact with the incoming molecules. Right? So this particular flow regime we can call as free molecular flow, where this happens when your lambda is equal to one or more than one. Right? Now, so there is a need for change in governing equation in this flow regime, and the kinetic theory of gases finds its applications in hypersonic flights at especially at higher altitudes, right? So from these specifications, we can say that the hypersonic Mach number or hypersonic flow regime is something which is very much greater than one, correct? So low density flow itself is one of the definition for hypersonic flow, along with all other parameters. But we said one or two of this phenomenon occurs, then we can say that it is hypersonic flow, right? So now comes a problem again: low density flows and high density ratios. We know that we have a normal shock, right? Say at the nose, if you have a blunt body, to a certain extent we can consider that as a normal shock. And for a calorically perfect gas, we can say that at high Mach number, the density ratio ρ2 by ρ1 is very high. So we consider, say, it would reach up to 6, right? So at this point, if concerned fluid is chemically reacting mixer or even thermally perfect, then the ratio increases to a value of 20 even in the case of Apollo flight, right? So low density flow, which talks about only the density of the flow, and there is a discussion on mean free path and the characteristic length and the definition of Knudsen number. But here we consider a high density flow. The high density ratio, not the flow, high density ratio because of the normal shock. And for example, Apollo, we have this ratio to 20. So now there is a problem. We cannot simply simulate this in the laboratory scale. Like we run one full day of low speed wind tunnel and 30 seconds of supersonic wind tunnel. We cannot do that particular experiment of hypersonic flow in the laboratory scale because you see it is difficult to achieve this flow with very high kinetic energy, high Mach number, without the change in thermal properties of the fluid, right? So, for experimental simulation, we use one particular solution, which is like, we use the gas which is different from the air. Say, it should have the low specific heat ratio. Say, for example, we consider tetrafluoroethane, which is having a specific heat ratio of 1.2, and hexafluoroethane, whose specific heat ratio is 1.1. So if we use this gas, we can achieve the required hypersonic criteria, right? So low density flows need to be considered strongly for the hypersonic flow phenomenon and its calculation. So I stop at this point, and we know we have studied the hypersonic flow phenomenon like thin shock layer, entropy layer, viscous interaction, high temperature flows, and low density flows. At last, we have studied something called high density ratio, right? Rho 2 by rho, right? So that's all. I stop at this point, right? Thank you very much. We will meet in another presentation. Thank you.